Welcome. My name is Ron Papa Schmidt, and I'm the creator of the Net Zero Now YouTube channel. This is going to be video 8D, and the title is going to be 2026, January 23rd to 27th, North American Winter Storm. So let's begin. I'm going to begin with just an explanation about the title, okay? So the title really comes from the nomenclature or how Climate Central is going to track this storm. They track storms that are over $1 billion, and this is the official designation that they are using. Now, it turns out that there's also the Weather Channel, which tracks storms, and they start tracking storms earlier than Climate Central does. And when they see a major storm, they give it a name. In this case, they gave the name Fern to this storm. And they have slightly different dates. They call it Winter Storm Fern, and they started a little bit earlier and ended a little bit longer for reasons I'm not quite sure why. Now, I'm also going to include in this video one other storm that happened right after that, from January 3rd to February 2nd, because to most people, it would seem like this was just one storm. But that storm was given a separate name, and it was given a separate name by the Weather Channel, and it's called Gianna. And so in this presentation, I'm going to talk about both of those. And I decided to, since I've done one presentation already where I talked about the 2025 U.S. climate disaster events using the information from Climate Central, and they're going to be doing another update, their official update in the spring of 2026. And they'll provide more information about Winter Storm Fern, et cetera, and stuff like that at that point in time. I decided to stick with the Climate Central titles because I'm going to be doing a number of presentations, I envision. Probably each time Climate Central does a major report, they just sort of explain to everybody what is going on. So that's why I wanted to stick with that title. But for the rest of this presentation, I'm going to break it into two separate sections, as you'll see on the next slide here. First of all, I'm going to do an overview of what caused and the impact of Winter Storm Fern. And then I'm going to, the second portion of this presentation, I'm going to do an overview of the causes and impact of Winter Storm Gianna. And then finally, in the third section, I'm going to talk about climate change and how it impacted both of these winter storms. So that's what the presentation is going to be about. So let's begin. And we'll begin with what caused Winter Storm Fern. And as it says up here, Winter Storm Fern, really I went from, I'm using now the Weather Channel dates, okay, from January 22nd to the 30th. It was sort of a historical storm because it was really a rare alignment of a couple things. We had a polar vortex and what they call the triple threat moisture sources that sort of made this such a mammoth storm. And so the first thing I want to talk about is what triggered it. And what triggered it was a disruptive stratospheric polar vortex. Now, I'm going to go into that in a second, okay? Now, I did a separate, and I just recently released, at the same time I did this video, video 12D called Polar Night Jet and Polar Vortex, which is sort of a deep dive, sort of scientifically oriented presentation that sort of explains what's happening in the stratosphere and the troposphere and why we have what we call polar vortexes. And I thought I would just show you some of the illustrations I have in that presentation before we get into the rest of the material, because it's really, there's so many words back and forth here. The wordsmithing of it may make it a little bit difficult to understand. So I think maybe pictures might help a little bit. So let me digress to that first before we begin with this slide. And again, it's available. We explain this in much more detail in that particular video. So in the upper left-hand corner, when you hear the term, jet streams or polar jet streams, and you hear the term polar vortexes, there are really two of those. Okay, there is the stratospheric polar vortex and what is called the polar night jet. That's that blue area circle up on top in the stratosphere. And then down on the troposphere, which is the area of the atmosphere that affects us most, our daily living, we have what is called the polar jet, which we've talked about in a number of presentations now. And then the polar vortex, which would be the area within the troposphere, sort of inside the polar jet. Now, if you look at the right-hand side, you can see an illustration of what the polar night jet looks like and the stratospheric polar vortex. Okay, think of it as you can see here, it's a long cylinder of rapidly moving wind, particularly on the outside. And it starts about 10 miles up at the beginning of the stratosphere, and it can go up as high as 30 miles, maybe even a little bit higher than that in certain circumstances. And for terminology to have this make sense, is that when you see the outer edge of that, that's where the fastest wind is. And the outer edge is sort of bounded by what they call the polar night jet. And then inside of that, all of that massive air inside of that is referred to as the polar vortex, in this case specifically the stratospheric polar vortex. Now, the same thing exists in the troposphere, and there it's called the tropospheric polar vortex. That is the air that actually does come down and affects us. And it's outlined, the outer edge of that is the polar jet. And that jet is not, so many of the pictures you see sort of make it look like a tube, but it's really not. It's a big wall of air, as you can see from the illustration here, for the stratospheric polar jet. So that hopefully will help you understand that a little bit. And then that stratospheric polar jet and the stratospheric polar vortex influence the behavior of the tropospheric polar vortex and the polar jet. And so if you can see on the picture on the bottom, when that is stable, that means it's moving very rapidly. The pressure of that, the speed of that, etc., helps control or contain the polar jet, and as a result of that, the tropospheric polar vortex, which for the rest of this presentation, generally when you hear me say polar vortex, I'm referring to the tropospheric portion of that, okay? And then you can see when the stratospheric portion on the illustration on the bottom right-hand side, you see a disrupted polar vortex. When that happens, it gets disrupted like that. What it does, it loses energy, it warms up, and as a result of that, it frees up or it causes the polar jet stream to meander much more, and the polar vortex, then the air inside of it, then goes much further south. And that's what we experienced in this stage. Now, to quickly summarize that table, you can see I've got over here the stratospheric polar vortex and the tropospheric polar vortex. I've got the altitudes, the wind speeds, the boundaries there, which really sort of represent the polar night jet and the polar jet, the wind direction. They're all counterclockwise. The season, the stratospheric one really just occurs in winter, and it occurs because of the tilt of the Earth. And as in wintertime, as the tilt causes the pole not to get any sunlight. That's why they call it the polar night jet. It gets very cold up there, and that's what allows this to form. Whereas the tropospheric one is there year round. And then what do we feel? I mean, so we have, while the stratospheric polar jet influences significantly the behavior of the tropospheric polar jet, we do not feel any of it. We feel it through the behavioral change in the tropospheric polar jet. And that's where we get this rain, snow, cold snaps, and other kinds of things. So hopefully that, whatever you call that word salad or whatever you want to call it, that makes some level of sense to you. So let's now continue on to the actual presentation. Trust me, it's going to get easier from here, okay? So let's go back to the slide that we talked about before, okay? And we talked about how the trigger was a disrupted stratospheric polar vortex. And so the catalyst was something called a sudden stratospheric warming event, an SSW. And what that does is it causes the polar vortex to weaken, as I mentioned before, and elongate it. You can see that sort of elongation that occurred in the illustration we just had in painted shape. Okay, the squeeze. So when that happens, what that does is then sort of that weakens the polar jet, and then that in turn causes this air then within the polar jet or the troposphere to then sort of head into central and eastern United States. So it starts moving southward. And the result of that was an Arctic blast. In this case, temperatures dropped by 30 degrees to 40 degrees below normal. Now, the second cause I mentioned briefly the first slide was that what they call a triple moisture collision. And this is sort of like these three sort of events happen. So let me talk about that first, because they occurred at different times to sort of strengthen and continue this storm. One was a specific low, and then the storm that sort of originated from this came off the west coast, off the Baja Peninsula, and then started heading towards the mainland. This was, and this took subtropical moisture from the west coast there. And really, it's almost like you saw these atmospheric rivers that occur periodically in California. This wasn't an atmospheric river, but it's similar, where massive amounts of moisture then moved into the southern part of the United States. As it did that and started moving towards the plains, because now we remember in west where the wind speed and how the wind flows is from west to east rather in the United States. And they call that westerlies because it's coming from the west. So as it got to the mid-plains, there was exceptionally warm water within the Gulf of Mexico, and as that warm air and moisture started coming up, it provided a massive reservoir of additional humidity. So we had the humidity from coming from the west coast, like from the atmospheric river, and then it gets met with the humidity of this warm water from the Gulf. That provides, again, a substantial reservoir to sort of keep these storms going. And this is really, below that is just a note, but it's a really important point. For every 1 degree warming Celsius that we have, the atmosphere holds 7% more water. And we've talked frequently, and I'll show you at the end, how temperatures are going up, right? What that means, we have more moisture in the air. What does more moisture mean? We get bigger storms and more frequent storms, okay? And it's just common sense. And then the other thing that happened, as it started reaching the East Coast, we had a nor'easter. And this brought in more water. Nor'easter is like, we think we talked about hurricanes, right? I think everybody's seen a picture of hurricanes. We can see you have this counterclockwise massive movement of air around an eye, which in the case of a hurricane is warm or hot. The difference here in nor'easters is that the core is cold. It's not quite, the rotation isn't quite as fast, but frequently they're significantly wider. And so what happens, since it has a counterclockwise motion, as it moves up the coast, What it does is it takes moisture from the Atlantic and moves it inland because of the counterclockwise move of this moisture rising. And that can add substantially more water to it. And I haven't quite finished this one, but that'll be one of the next ones I'm going to do. It's going to be 11A. It's called an extratropical cyclone, and all that means is the difference between an extratropical and a tropical cyclone or hurricane. It's just that it's got a cold center. And nor'easters would be a type of one of those. So hopefully that's understandable too. Let's move on to the next section here, okay? The third cause was we sort of had a catastrophic layering of ice, which was very destructive in the South. And here they have another interesting scientific term. I don't know who comes up with these, but they call it the warm nose, okay? And I have an illustration that probably explained it better than what I've got up here. So what happens is you have this cold air that's coming from west to east, and as it hits the mountain range, like particularly in this case, it would be the Appalachian mountain ranges and stuff like that. What can happen is that cold air will then, some of it will go up and stay a little bit higher, and some will stay down and follow the mountain. At the same time, you can have warm air coming in from the coast, and some of that warm air gets under the cold air, and you can see that red thing there is what they call the nose between those two white lines. Okay, looks like Pinocchio, right? And so what happens, you have snow coming from the tropic cold area. It gets into this warm air, and it sort of melts. It warms and turns into rain. And as the rain is getting, but now it's so close to the surface, as it starts hitting this cold mass again, it starts freezing up, but it doesn't have time to turn and show, so it turns into the sleet or rain stuff, and that's why we get these ice that exists in a number of these areas in these storms. That's one of the reasons for it. It's really caused by different layers of area of cold, warm, cold. And in this case, you could accumulate, I think they accumulate in some places like in Louisiana and Mississippi, 3/4 of an inch of ice. And it caused over 1 million homes to lose power, etc. So that's sort of the technical side of this presentation with regard to Fern. So let's get into the impact. Okay, what did Fern do? Well, it cost us 153 lives for number one. And two, there were major power outages and grid failures. There were over 1 million customers that lost power at the peak of the storm. We had significant ice damage and huge strain on the grid. And sometimes they had to go buy additional power at a very expensive kind of rate. And you can see in an illustration up here, is Nashville, Tennessee. I thought I would just show you can see where trees had fallen down, power lines were down, etc. from the ice. The next kind of economic destruction we had was economic and infrastructure damages. The direct losses that they had as of February, I think it was as February 3rd, was somewhere between $3 to $4 billion to maybe up to as high as $7 billion. Some estimates had. That number should grow dramatically because it doesn't incur non-insured losses and some other kinds of things. And Climate Central will probably issue that information in their report in the spring of 2026. And there was, so the damage will be a lot higher than the number you've seen here. And then there were lost oil production for a couple of days, or flights canceled, et cetera, and stuff like that. And there was record-breaking snowfall and tornado outbreaks and all those things. And I think to really get a scope of this thing, I saw this illustration here of how it affected different areas. And you can see it had snow, and then it had heavy snow, which hit a good portion of the United States. And under that, you had sort of a wintry mix, a combination of, really heavy snow or slush or sleet or things like that. Then you had ice storms underneath that, and then thunderstorms further south. But look at the scope of that across the United States as this thing moved across the country. So that sort of wraps up Fern. So let's move quickly to Gianna. So what caused Gianna? Well, okay, Gianna was what they call a combination. It was sort of a powerful bomb cyclone and a nor'easter that struck the eastern part of the United States. It really, the connection here is from a polar vortex perspective. Is the storm was driven by the same disruption, the the stratospheric polar vortex that we had in Fern. Fern was the initial surge of that. There was a secondary wave with Gianna. And again, I've listed the video that I have that will explain that in more detail. Then the other thing that happened is it sort of had this atmospheric collisions this cold Arctic air collided with warm moist air from the Gulf Stream in the Atlantic Ocean. And here's a picture. This is a heat map, which sometimes shows that how hot the water can be in the Gulf Stream. You can see it going up Florida, going up the East Coast. That's sort of a temperature map with red being the hottest. Okay, the third thing is in the jets, it's a jet stream interaction. And in this case, you had a high velocity. This was a subtropical jet, not a polar jet, but a subtropical jet interaction that resulted in a lower pressure system dragging the storm along the East Coast, eastern seaboard. And I talk about all the jet streams and how they work together in sort of an overview presentation, 12A, called Jet Stream Roulette, which is also available at the same time this video is available. So if you're interested in how jet streams work, I would highly recommend that particular video. And they are, let me tell you, jet streams are extremely important. That is fundamentally probably the most important thing that determines what kind of weather patterns we have here on Earth. And then we had, in addition to that, they had a bomb cyclone. And all that means it was a typical cyclone, just like I talked a little bit about before. I see a picture here on the right, looks like a hurricane to some extent. It's a very large counterclockwise movement around a core, okay? It's just that in this case, they call it a bomb cyclone because the pressure drops so quickly. In 27 millibars in 24 hours, it's like this thing just happened like a bomb going off of the air. So that's why they use that term. They also have other terms they use, like they call it an explosive cyclogenesis or a bombogenesis, etc., and stuff like that. But they're all basically the same concept. Okay, some of that just has to do with the speed with which it occurred. And then here's the impact. Again, there were at least 10 casualties. There were 190,000 customers that lost power. There was record snowfall. There was damage to infrastructure, transportation chaos. Here they had over 100 car pile up on I-85. There was coastal destruction. Part of that, because as sea levels get higher, what's happening, you have more storm surge also that can occur, and that collapsed multiple oceanfront homes. Aviation flights were canceled. You had agricultural damage, frozen. And probably a new one that I don't remember occurring here before is that we had that sort of caught the attention of everybody, and that was called cold stun iguanas, where iguanas were falling from the trees in Florida, etc. Now you can see pictures in the upper right-hand corner of that. You can see the example of a traffic jam, the ice in the streets, the damage being done on the ocean shore where houses were collapsing and an airplane being de-iced. So that really quickly covers Gianna. So let me talk a little bit more about how climate change is affecting that. And so here's some of the basics of climate change we've covered before, but I just think it's so important that you understand this, okay? Number one, if you take a look at chart number one, it clearly shows temperatures are increasing. At the same time, carbon dioxide is increasing, and that's true of all greenhouse gases, which is really telling us the reason that temperatures are rising is because of the level of greenhouse gases we have in the atmosphere. I've got whole presentations that talk about that. But so And here's another example of rising temperatures. You can see how temperatures are rising. You notice they're rising fastest in the Arctic, second fastest over land, and third fastest over ocean, but in all cases they're rising. This rising differential then is referred to as Arctic amplification. That's a term that's frequently used in some other presentations. And what it really means is the temperature difference between the temperature at the pole and the equator is shrinking. And almost as I've gotten into this science and doing these presentations and things like that, the thing that I'd never really understood before is how important temperature differentials are in terms of all the winds and patterns and how all these things work. And so as these temperature differentials change, it has a profound impact on our weather, etc. The bottom one just shows the obvious one I talked about earlier, that yes, moisture is increasing along with temperatures. And on the lower right-hand side is one I just released, which shows again, it shows the history of billion-dollar storms in the United States, severe storms in the United States. And you can see they are clearly going up dramatically, and they're following the curve of temperatures. Why is that? And by the way, with these billion-dollar storms, Climate Central, when they do this, they go back and adjust everything for inflation. So if a storm occurred in 1980, they go back and readjust that to 2025 inflation numbers or CPI numbers. And therefore, what you will see over time, we may see more and more billion-dollar climate events in the 1980s, 1990s as inflation continues to increase. So these numbers are consistent in that fashion. Last thing, I went ahead and I listed just some of the major drivers that affected these particular storms. If you look at the columns, I got what the driver is, like the first one's the polar vortex, the elongation. The impact on Fern, its rank, how important was that to Fern? And then the impact on Gianna, and how important was it there? So the polar vortex was really the number one factor for Fern, but it turned out to be the third most important factor in terms of Gianna. The most important factor was the ocean heat content, and that's what really caused this biocyclone. That was that was important for Fern. It was fourth. It was number one for here. And so if you take a look at the top five, they were all the same. And we talked about the vortex already. We talked about atmospheric moisture, the more moisture in the air, obviously. That was second for all of these. The more intense and stronger the storms are going to be. That just makes sense. Jet stream meandering was a little more important in Fern because of the role that the polar vortex played. And then ocean heat content was the number one thing for Gianna because it was so close to the Gulf, to the Atlantic Ocean. But it was still important for Fern because it brought the moisture up from the Gulf of Mexico, and then you have thermal shifts, or the ice belt is sort of changing and it's moving. And so that also influences it. And if you're really interested in this, spend some time looking at it. I just wanted to give you a quick sense of some of the major items, the top 8 items that affected both of those storms. I just wanted to show this one real quickly. I just want to make a point. See the polar vortex, it's still going on. This is a projection of what was going to happen to our weather later, over about, I think, near Valentine's Day or something like that, or a little bit before that. In the United States, the polar vortex was still there, but now we have a Greenland blocking high that's going to mean that a good portion of the eastern and Midwest is going to go to exceptionally high temperatures. And the only reason I want to show this is there's so many variables that come into play here that determine what our weather is at any one point in time. The fact that we know that climate change is impacting the polar vortex, and you're going to have more of these, but it doesn't mean it's always going to hit the United States. So there's a lot of variable here, and that's why when I talked about jet streams, I actually use the term roulette to just sort of get everybody get a sense of the amount of variability that's involved here, because there's so many different elements that influence things. Before I close, I just want to show this slide again. And I've shown this a number of times, and this is what the client scientists say are going to happen. We hit 1.5 degrees at the end of 2024, and they said there would be significant economic, environmental, and social impacts, and I think we all saw there were. They said if we get to 2%, the world will see likely catastrophic and likely irreversible damage. I think you can see, just look at how much worse things are getting in 25 and 26 versus where we were before. I think it just points out, screams at us the evidence every single day that this is a real problem, and they're right. And you can see, maybe get a sense of, oh, if we have one of these polar vortexes all the time, followed by hurricanes all the time and other things, yeah, I can see where this could really make life really difficult here on Earth. And I've got other videos I'll talk about, so that's enough on this slide. Let me just wrap this up. So we talked about what caused an impact, the Winter Storm Fern in Gianna, and how climate change impacted that. I got a little bit of my Eagles one of my favorite Eagles songs, just an attempt to sort of encourage you to get out and do something about this, folks. It's real. And some things you can do, and I've talked about this a number of times. Almost every video is vote. I mean, when I talk about it in these videos, again, I'm talking about it from a systemic perspective. And that means it's got to be solved at the governmental level, major corporate levels, and it's got to involve all the leaders, major leaders in the world. We've got to work together cooperatively to do that. And the only way we're going to get the net zero from, and the only way we're going to just prevent a disaster for our kids and grandkids, is we need to get the net zero greenhouse gases. And the only way to do that is we got to elect the leaders in every single election at every level of government who are committed to climate change, that recognize this as a serious problem. And on top of that, they need to have the personality and attitude and inclination to work together with other people, because we've got to work together to solve the problem. Other than that, subscribing would be wonderful to this channel. Talk about it, tell other people about it. And there's all kinds of personal actions you can take. I didn't cover any of those in this video. I will at some point in time create one, but you know, when you all get involved in recycling, turn our thermostats down, period, a whole bunch of things we know. So thank you very much for your time, and have a great day, and hopefully you'll join us for one of the other videos.